Hello again and welcome. Today we're going to be talking about through termination. This is a topic that comes up from time to time. It came up again recently. There's a member on EEV blog that goes by the name of Graybeard, and he made a video where he showed several different terminators of various qualities and cost. And in the end, what he was showing is once he connected his terminators to the oscilloscope, any differences that he saw with the VNA were minimal. So what I'd like to do in this video is determine if it's possible to improve these terminators. Now back in 2016, I had posted a thread where I used my HP8754A vector network analyzer to modify one of these through terminators. And this is the one that I came up with. So this has two 1206 resistors in parallel. This is another one that I tried. This is four 200 ohm resistors in parallel. Again, these are 1206s. And when I compared all three of these, I did see an improvement in the return loss. When Chris had started that thread, I had posted a link to my original data, and he was quick to point out that I never attached these to an oscilloscope and how that was going to mess up the return loss. So of course the obvious question is, why didn't I attach these to an oscilloscope and then measure the return loss? For me, the answer to that is pretty simple. All of the oscilloscopes that I own support a 50 ohm internal termination. So this is looking at my LaCroix 64XI. You can see all the inputs are 50 ohm selectable. You can measure a maximum of 5 volts RMS when that's selected, or they have a 1 mega ohm in parallel with 16 picofarads where they can measure less than 400 volts peak. This 64XI has a bandwidth of 600 megahertz. I also own a LaCroix Wavemaster 8500A that has a bandwidth of 5 gigahertz, and that scope only has 50 ohm inputs. My first DSO, which is a LaCroix 7200, I still own that scope, and that scope's 4 gigahertz inputs are 50 ohms only as well. So I'm not normally attaching a 50 ohm terminator to my oscilloscope in the first place. So if we look at Graybeard's data, again, he measures all of his terminators open circuit, he connects them up to the oscilloscope, and you can see essentially a dramatic difference in the return loss. And assuming we need, say, 20 dB of return loss, we're basically limiting the scope's bandwidth to about 60 megahertz. 20 dB is a VSWR of about 1.22 to 1, or about a 1% reflected power. So here I'm looking at the DC resistance of the different terminators that I have. So this is the Pasternak PE600850. You can see it's 49.8 ohms. Next we have the two 1206 resistors. This measures 49.8. Then I have my four 1206 200 ohm resistors. You can see that one is 49.945. Then I have another one, it's called 64XI. That one measures 49.970. Then I have two other ones. This one at the bottom is the actual oscilloscope. That measures 1.0001 mega ohms. Then we have the 64XI Sim. So this is my oscilloscope simulator. And you can see it measures 1.0017 mega ohms. So this is the one that we're going to be focusing on, the 64XI. And that's this device here. So this is a terminator that I made just to work with this oscilloscope. So when we're talking about through termination, I want to be very clear. It's not a series resistance. Rather, it's a shunt. So for a 50 ohm terminator, we're talking about adding that resistor between the center conductor and the ground. One of the common things people will show is they'll take a BNC like this, and they'll take their 50 ohm terminator and they'll attach that to one link like this, and then they'll use this for their terminator. Just consider that you're adding this length of stub, so that's a discontinuity, versus a through terminator like this, where the conductor is continuous, and then we're placing that terminator inside of the transmission line. So let's just try a real simple experiment. What I'm going to do is take my RF signal generator that has a 50 ohm source, and we're going to split it into two signals, and we're going to apply that to two input channels of our oscilloscope. One of them is going to be selected for 50 ohms, the other one will be selected for 1 mega ohms, and we'll be applying our through terminators, and let's just see if there's a difference between these two signals. Now, I want to be very clear, when you go to split a signal, you wouldn't want to use a T like this with two pieces of coax on the backside. If these two pieces of coax are 50 ohms and they're 50 ohm terminated, and we got 50 ohms coming in. Well, this is not 50 ohms that this is seeing at this junction. It's going to be 25 ohms ish. So we have to do this with a resistive splitter. Again, a T is not how we split signals. So for this demonstration, we'll be using a resistive splitter. This particular one is good for DC up to 4.2 gigahertz. So again, we just have our splitter. This input port will be going off to our signal generator, which is attached to this piece of coax here. And for starts, we'll use our Pasternak terminator. And I'm just going to set the amplitude so we're about one division down on the top and bottom. Right now you can see both channels are right on top of each other. I'll just go to a dual grid. So channel 1 is our yellow trace, and you can see it's set for 100 millivolts per division, and I've selected the 1 mega ohm input. And for channel 2, you can see it's also set for 100 millivolts per division, but I've selected the internal terminator. We'll just go back to a single display. Now currently our RF generator is set for 1 megahertz. Let's go ahead and we'll increase the frequency. Here we are at 180 megahertz. Let's just do measure, and we'll do standard horizontal. And you can see our period is roughly 5.5 nanoseconds with a frequency of about 180 megahertz. But notice again, there's a slight mismatch between these two. And you can see as I continue to move up in frequency, so this is currently about 450 megahertz, that the difference between these two signals increases a fair amount. The other thing I want you to pay attention to is the signal off of channel 2. Again, channel 2 is going into that input that has the 50 ohm terminator. I'm just going to turn off channel 1 for right now. So you can see I've set my RF generator to sweep. Let's just zoom out a little bit and look at how the amplitude of this is changing. The obvious question is, we have this Marconi RF generator as a 50 ohm source. It's going to this 50 ohm splitter. Channel 2 is attached to the input of the scope directly, which is using its internal terminator. So you may ask, well, where's really the problem? Why is this changing so much? Well, the problem again is because of the terminator's mismatch. So let's think about this a little bit. We have a signal generator. It has a source impedance of 50 ohms. It's going to this resistive splitter, which has a drop of 6 dB or half. One of the outputs is going through our Thru terminator into channel 1, while the other one goes directly into channel 2, which has our internal termination. So if there's a mismatch on this channel, that signal reflects back into our resistive splitter. Part of that signal is going to get reflected back to the signal generator. The other is going to be sent down to channel 2. So having this mismatch is actually going to cause an error on our channel 2 measurement. So let's just prove that. What I'm going to do is take off our two pieces of coax, and what I'm going to do is attach these two devices in series with the output ports of our splitter. I'm sure that there's a few of you already know what these two devices are. They're a 6 dB attenuator. So combining that with our 6 dB resistive splitter, we have a total loss of 12 dB per channel. So what's the purpose of these? Well, it's basically isolating the two channels from one another. So now as channel 1's mismatch changes, it's going to have less of an effect on channel 2. So again, we've got our splitter, and now watch what happens when we connect channel 2. You see how flat the amplitude is? That's just because we've introduced these two attenuators that's helped with the port match on channel 1. That's all we've done. Let's just go ahead and detach our Thru terminator from the oscilloscope and see if we see any change in channel 2. You can see if there is, we really can't see it with the oscilloscope. Let's go ahead and we'll remove these two 6 dB attenuators. Now on the oscilloscope, what I've got is this orange trace, and that's the difference between these two channels. Let's go ahead and connect channel 1, and we can see there's a slight difference between these two channels. Now currently the RF generator is set for 180 megahertz. Doesn't really matter. I'll change the difference from 100 millivolts per division to 50 millivolts. Just amplify that up a little bit. Now let's go ahead and swap out our terminator and see if any of these reduce the difference or make these two signals match up a little closer. So again, this is the original one from Pasternak. Let's start with this one. This is our two 1206 100 ohm resistors in parallel. And you can see there really is no difference between the two. Now let's try our four 200 ohm resistors in parallel. Again, these are 1206 parts. And again, you can see there's really no difference between them. Now let's try the one that I made for the 64XI. And you can see it's a lot better. Let's just do File, Save Waveform, and we'll do Math and Function 1, save it to Memory 1, Save Now. So the yellow trace here is what we're looking at. And again, we'll attach our Pasternak part and look at the difference between the two signals. So this terminator that I specifically made for the 64XI somehow has a better match than these other three. But keeping in mind again that we have the 60B splitter in play, so this is masking what this mismatch is actually looking like. We can get a better idea what this mismatch looks like by using another piece of equipment, which is a vector network analyzer. Again, originally when I made these measurements, I was using an old HP 8754A. That network analyzer was made in the 1970s. Since then, I've purchased an Agilent E8557A. That analyzer was made somewhere in the 2000s. So I've gone ahead and I've made several measurements with that network analyzer. Let's start by looking at these with no load attached. So the terminators are not attached to anything on the backside. So this is looking at the return loss. Again, lower is better. So the orange traces of the Pasternak. The black and the brown are where I've rebuilt the terminator using 1206 resistors. But notice this red trace, it's quite a bit worse than the other three. That's the one that I've specifically made for the 64XI. You may be looking at this and saying, wow, you know, that's the worst of all of them. But I just showed you that it's not. It's actually the best one out of them. Let's see what these look like attached to our oscilloscope. So here I'm looking with the oscilloscope set to different input voltages. But if we look at the difference between the two, it's really not significant. We're talking about a half a dB. So if we look at our Pasternak terminator with the scope set to 2 volts per division versus 500 millivolts per division, you can see there's really not a whole lot of difference between the two. The same thing for our 200 ohm resistors in parallel or our 4 200 ohm resistors in parallel. So for this particular oscilloscope, it really doesn't matter which range I'm in. So let's just focus on our 500 millivolts per division. So if we look at our Pasternak terminator along with our 200 ohms and our 4 200 ohm resistors, you can see the two terminators that I made have a little bit worse performance than the one that was originally sold by Pasternak. Let's see how these compare against the one that I made specifically for the 64XI. So the 20 dB point now is somewhere up around here, maybe 50, 60, about 70 megahertz. So why is this terminator better than the other three? So to help answer that question, I've got one of my original college textbooks. This is Boldstat, and this is Series Parallel AC Networks Introduction. This is what you would typically learn when you go to college to become a double E. This chapter is followed by Methods of Analysis and Selected Topics AC. You can see we have mesh, a lot of scary formulas, but this is all the basics of AC analysis. Those we're talking about omega L, ooh, scary stuff, and Z's. The next chapter is network theorems, AC. So let's just go over some of the math. So let's just start with our basic circuit. We have a 1 volt signal generator, and it's set for 350 megahertz. It has a source impedance of 50 ohms. And then on the right hand side we have our oscilloscope. And we said for the 64XI, they say it's a 16 picofarad capacitor in parallel with 1 mega ohms. So for now, let's ignore this 1 mega ohm input. That's why I'm showing this in a dotted line. And let's just focus on this 16 picofarad capacitor. So the first thing we're going to do is calculate the impedance of the capacitor at 350 megahertz. So that's X sub C is 1 over 2 pi FC, or 1 over 2 pi times the frequency, or 350 megahertz, times the capacitance, or 16 picofarads. That gives us a value of 28.421 ohms. So you can imagine that in parallel with our 1 mega ohm, assuming no parasitics, that this 1 mega ohm really has no effect. So what's the total impedance that our 1 volt source sees? It's going to be the 50 ohms plus our 28 ohms. But it's not quite as simple as adding these two. You have to add the vector. So to do that, we take the square root of X sub C squared plus R squared. So it's going to be 28.421 squared plus 50 ohms squared. And then we take the square root of that, and that gives us 57.513 ohms. So if we want to calculate the current through this network, it's going to be V, or 1 volt, divided by Z total, or 17 milliamps. If we wanted to know the voltage drop across our 50 ohm resistor, we can take that current multiplied by the pure resistance, or 17 milliamps times 50, and that gives us a value of 0.869 volts. Calculating the voltage drop across the capacitor, again it's the current times X sub C, or 17 milliamps times the 28.421 ohms, and that gives us 0.494 volts. So if we take the voltage drop across VR plus the voltage drop across VC, that's 0.869 volts, we said, for the VR, plus 0.494 volts. That doesn't equal a volt. So what's going on here? Again, remember the vectors. We have to take VR squared plus VC squared, take the square root of that, and that equals 1. So with a 1 volt source at 350 megahertz, V sub C is equal to 0.494 volts. Remember that. This is looking at LT Spice. This is a free Spice simulator. You can see we have V1 as our source. It's a sine wave. For AC analysis, it's going to output 1 volt. It's in series with a 50 ohm resistor R1. And then that goes off to our 16 picofarad capacitor in parallel with our 1 mega ohm. Again, so C1 and R2 are the input impedance to our oscilloscope. So we're going to look across the voltage of the capacitor, and we're in dB right now. Let's take a look at this in linear mode. You'll see as I move the cursor across our green trace in the lower right, we're displaying the voltage as well as the frequency. So this is at 65 kilohertz, and you can see it's outputting roughly a volt. As I move the cursor across to the right, you can see we're now at 350 megahertz at 492 millivolts, which again, what did we calculate? 350 megahertz, 494 millivolts. So our Spice simulation is quite accurate. Again, we've included the 1 mega ohm resistor as part of our simulation, and you can see it's not really having any effect on our result. So let's go ahead and fire up MicroCap, which is another free simulator. And again, you can see it's basically the same circuit with our source in series with our 50 ohm resistor and the 16 picofarad in parallel with our 1 mega ohm resistor. We'll do analysis and AC analysis, and again we'll sweep from 10 kilohertz to 350 megahertz. And let's go ahead and just hit run. And again, as we move the cursor off to the right hand side, you can see we're at roughly 346 megahertz, and again the voltage is roughly 495 millivolts. Again, very close to what we've calculated. Let's go ahead and we'll insert another resistor. This is going to be our Thru terminator. We'll keep that at 50 ohms. We'll just attach it to ground like so. So again, here's our oscilloscope, here's our 50 ohm Thru terminator, and here's our signal generator on the left. Let's go ahead and run our AC analysis. Let's turn off our V drive, and now we can go ahead and select run. Now let's move our cursor off to the right. You can see again at 350 megahertz, instead of being 500 millivolts, We're now all the way down to 375 millivolts. So just adding this termination resistor has greatly improved the flatness of this. So can we make any other changes to this circuit to help improve this? So here we have the exact same circuit, except notice that I've introduced a small inductor in series with our 50 ohm termination resistor. You'll also notice I've included a few different cards for S11, VSWR, and then also the return loss. So let's go ahead and we'll run our AC analysis on this circuit. And what I've done is I've enabled stepping. So I'm going to step L1 from 5 nanohenry to 60 nanohenry with a 5 nanohenry step. And now let's look at VC. Notice depending on the inductance, the voltage either goes up or it goes down, or there's one here where it's flat. And that's with L1 set to 15 nanohenries. Let's take a look at the SWR. Here's the return loss. And here's our Smith chart. Let me just show you a few photos of what this looks like inside. For the inductor, I'm using these parts from Coilcraft. These are an 0805 package. But what happens if we attach this terminator to an oscilloscope probe? This one happens to be made by LaCroix. This one is a PP005A. This is a 10x probe rated for 500 megahertz. So again, this is looking at our Pasternak terminator. And here are the two modified ones with the 1206. But now let's compare that against the one that we modified for the 64XI. If we consider 20 dB as our cutoff for the return loss, you can see we've gone from 50 or 60 megahertz or so. We've now increased it to about 180 megahertz. So a fairly significant improvement. If you're working with high-speed signals though, you're probably not using a through terminator like these, and you're probably not using a 10x scope probe like this. Normally what you're going to do is use resistive probes. This is a LaCroix resistive probe here, which is essentially, think of it as a piece of coax with a resistor at the tip, and that sets the divide ratio. Or you'll use some kind of an active probe like this one here. Of course, probes like this, first of all, are quite expensive, and then they're not generic. They're not made to just plug this connector, for example, into any old scope. This is made by LaCroix for their oscilloscopes. There's a member on EEV blog that's developing an active probe for sale. I don't believe that's available yet, but I believe he's still working on it. And that probe is DC coupled, and I think he's targeting 2 gigahertz with that particular one. I'll give the link for that in the description. I believe this targeted price too was maybe $200 or something. I had a little discussion with that guy about resistive probes and homemade ones, and he was talking about the repeatability of them and some other issues, and he pointed out that a lot of the information on resistive probes I had actually provided, but most of what I had shown for homemade probes really isn't something that I would normally use, where I was trying to embed, for example, the resistor inside of the coax. Just different ideas that I had, and none of those performed very well. So I could understand him getting the wrong idea that resistive probes may not work as well as what you would expect. So I went ahead and I made these two to give him an idea as far as repeatability, and then I made this one. I was running some experiments with the Wavemaster with this probe, and I think we were showing rise times maybe in the 30 picoseconds or something. Of course, the Wavemaster is not rated to show rise times that fast. Let's be clear about that. And to get those kind of rise times, I wasn't using a pulser. I think I was driving a filter maybe to get that. Normally for rise time measurements, I'll use something like this. This is a homemade driver, so we hook up the RF generator to the input here, and then we get a square wave out. This one happens to give us a rise time of about 0.35 nanoseconds with a 1.2 volts peak-to-peak signal. This is made by Tektronix for one of their oscilloscopes. This is a S52. You can see it outputs a rise time of less than 25 picoseconds. And I've just got a connector here that I attach this to a power supply to run it. Well, that's going to be it for this video. Hopefully you enjoyed it. Maybe you learned something from it. Again, I'm planning to look at a series of low-cost multimeters again fairly soon. All those meters have arrived because I'm pretty sure that none of those meters are going to hold up to my testing. I've gone ahead and purchased a meter that probably will survive my test and would actually make a pretty good meter for the double E's. Well, until the next video, we'll see you then. Later.